Welcome everybody. This is the Impossible Metals webinar series, and today I'm very excited to introduce Niels from SGS. Niels is the Technical Services Director, very much focused on hydrometallurgical as part of the Metallurgical and Consulting Division, and he's been spending a bit of time looking at how might we process polymetallic nodules. So really excited for Niels to share his wisdom. And just a reminder, if you have questions, please hold them for the end, and then you can raise your hand or you can type them into the chat, and we'll take as many as we have time for. So thank you very much, and Niels, over to you.
Well, thanks, Oliver, and welcome everyone. Good morning, everyone. This is a Google Meet, so I'm not very used to Google Meet. I don't see the chat, so Holly, if I can ask you these questions during or after the you manage the questions, because I'm not seeing them from where I am.
Absolutely.
But, yeah. Well, thanks for joining all, and hopefully everyone enjoyed the hockey game again last night. So some of you may be a little bit sleepy still because of that, but hey, we had a blast. Now, I'm talking about onshore processing of seabed manganese nodules, and I'm going to talk a little bit about some of the processes that are out there, and then also talking about a little bit of the work that we've done. And I always like to kind of join this up with the importance of de-risking projects, the role of piloting in this, and I'm talking about McNulty ramp-up curves. So I'm going to kind of weave these two topics together throughout this presentation. So I thought it'd be useful to provide just a little bit of background on myself and how I got to where I am right now, and it may just provide a bit of useful background how I got to the various kind of learnings and findings that I've got here. So I've got a master's in mining engineering in Delft University in the Netherlands, so hence the accent. I apologize. Moved to Montreal afterwards, got another accent there, and then started working at Lakefield Research, which is now called SGS. And it's kind of interesting that I think in my second week that I was working here, I got involved in nickel laterite processing as an operator on a laterite plant that was built, operated for a fairly long time, and is now mothballed. It's on care and maintenance just this year, in fact. Moved back to Europe in the early 2003, and became an R&D manager at a metal recycling plant, where I was responsible for evaluating kind of new non-standard feed materials into the plant there. Apparently didn't quite like being back there, so we moved back to Canada again, and rejoined SGS and got involved in all sorts of flow sheets, copper, nickel, cobalt, and what I call the UMS, scandium, niobium, tantalum, and then also in the rare earths, which has been a topic I've worked in probably for the last 10, 15 years. It's I call myself a rare earth enthusiast, and lots of UMS within the rare earths as well. Around 2014, I initiated a symposium that's dedicated to processing of critical materials, and it's a biannual event right now. It's part of the Conference of Metallurgists, and then something that I enjoy doing. Hence, I also happily agreed to do this webinar when Oliver asked me to do this a few months ago. About 2019, I got involved in looking at some other materials. I looked at black mass from the battery recycling industry, but also got involved in looking at deep sea mining nodules. And it was interesting at the time that I was working on kind of 3 projects in parallel. At the time, none of them, I think, knew that we were doing that, and now they all know. It's not a secret anymore. But we worked on TMC, we worked for a GSR, and then we also worked on a Kupion flow sheet. Okay. That's a way younger picture of me sitting on the right or standing on the right there. But what's interesting, it's the Boleo pilot plant, and I have some pictures of that plant a little later on in this presentation. So apologies, just a few kind of marketing style slides on what, and then a little bit of background on SGS. So we are the world's leading testing, inspection, and certification company. And I kind of like this slide here that explains, why this is so important and what is testing, inspection, and certification. And I like the top. Let's just see if I can get my cursor going here. Hold on a second, please. Yeah, there you go. So I like showing the or talking about the testing part, because this is really where I get involved here. And the top left paragraph is the most important one on the testing here. So testing reduces risks, shortens time to market, and you can read the rest yourself. But this is a concept that I incorporate in all of my presentations, and today is no different here. So a quick slide on a few more slides on SGS. We are the industry leader, like we said. We are 99,000 employees at the moment, lots of facilities and laboratories, 5 business lines, and the one that I represent is natural resources. I like putting this slide up as well because it kind of shows how we touch the life cycle of a mining project from exploration, feasibility studies. So this is the work that I do in trying to develop metallurgical processes that feed the various studies, how we're involved in the engineering, planning, construction, operations. We do get, and I do get involved sometimes in visiting plants, doing plant audits, that type of work, logistics, transportation, and ultimately we're involved in the closure of a plant as well. So I think that's it. What I wanted to say about SGS in general, and so we're going to really get into the meat of this presentation. So why this presentation? Those that know me, you may have seen this slide before, so you kind of know my opinion on this. So the harvesting of nodules has been frequently discussed at various deep sea mining conferences. I've always thought there's insufficient attention to the onshore processing aspect. So I've heard comments made in conferences like, oh, that's for someone else to solve, or hey, we'll just rent the plant, or other comments of that nature. But the same questions apply as with conventional ore deposits that SGS or myself and other companies work on. And that is, what is the process that we want to apply for treating this new feed material? What does it cost to build the plant, or what does it cost to operate the plant? What's the metallurgical performance? And that means recoveries, leaching efficiencies, reagents consumptions, all of that. And how do I de-risk? So I'll talk a little bit later today about about the nodules, what they are, how they're characterized. I talk a little bit about the flow sheets that are in the public domain, and we'll get into some of the internal research work that we've done here at SGS. And then probably the last third of the presentation is about de-risking metallurgical projects, and I will tie it back into deep sea mining style projects towards the end. Okay, so let's get going with this. I'm really talking about CCZ style nodules today, located in the Pacific Ocean. This is generally a fairly homogeneous material. Physical upgrading is challenging, and hence we're kind of stuck with a whole ore style treatment flow sheet. And hydrometallurgy is involved in all of the flow sheets that I'll be talking about today. Composition is shown here on the screen, and it's quite clear that manganese is the main component of the material. So how do we process this material is the key question here. So those that are aware of what's in the literature, you probably have seen comments around 3 metals flow sheets versus 4 metals flow sheet, and the 4 metals flow sheet would go after nickel, cobalt, copper, and manganese, and the 3 metals recovers only the nickel, cobalt, copper. Now, if all manganese present in the nodules would be processed into manganese sulfate, this is not practical and would flood the market. For example, a 60,000 ton per year nickel plant, which is a bit of the size of plants that are considered for these type of projects, it would produce close to 5 million tons per year of high purity manganese sulfate. If we want to refer, kind of benchmark this against existing or planned manganese sulfate projects, like referring to the E25 Butcherbird project, who are planning a refinery of around 130,000 tons per year of manganese sulfate. Obviously, 5 million tons per year would flood the market. The slide also shows that the majority of the revenue is related to nickel, cobalt, copper. Now, these calculations were made probably about 2 years ago, so they're probably a bit out of date, but the main conclusion is still valid. The slide also shows that the majority of the reagent demand is related to manganese and iron. So the conclusion is we need a selective flow sheet, selective against manganese, iron, aluminum, but that does extract nickel, cobalt, and copper. That's what we're after. So let's take a look at some of the process options that are out there in the public domain. So we kind of grouped here in different styles of chemistries. We've got the sulfate chemistry, the ammoniacal chemistry, chlorides and nitrates, and the highlighted ones are the ones that I'll be speaking about today. So that's the smelting and acid leaching that TMC is pursuing, reductive acid leaching that GSR is pursuing. We've done some internal work around high pressure acid leaching. By the way, the plant that you see on the right here is the Boleo plant that I referred to as during one of the first slides, so that that STF did pilot, and that is a plant that does use a reductive acid leach tracker. So I thought it was relevant to throw it on the screen here. Okay, so starting with the first one, this is the smelting acid leaching flow sheet that's been proposed by the metals company TMC. Includes a pyramid processing step to process the nodules and produce a matte and then a manganese silicate. So that's the outlet for manganese within the flow sheet. It uses a refinery to process this matte into copper metal, cobalt sulfate, and nickel sulfate. It claims to be a near zero waste production. And with that, I mean that the residues from the refinery are recycled back into the pyrometallurgical flow sheet. We were contracted late 2021 for the refinery testing, so not the pyromet part of the flow sheet, but the refinery a part of the work. Quite a bit of background was or has been presented in technical conferences, Conference of Metallurgists by TMC in 2020, 2022. The 2024 paper is a joint TMC STS paper. Matt Bowlby, who may be on the line, in fact, presented that one. There have been quite a few press releases. These were joint press releases highlighting the production of nickel sulfate, cobalt sulfate here. And then quite recently, there's been a few around their work at PEMCO, where they're bulk processing a 2,000-ton sample. And Matt, if you're on the line, apologies, I did steal one of your pictures out of a recent presentation that I liked. So just a few comments on the pyromet route. The nodules are mixed with a reductant, the flux, and the refinery residues, and fed into a rotary kiln. So this is the calcination step. And they recently just announced that a 2,000-ton sample has been processed at PEMCO. So this is in September. The calcine is then smelted in an electric arc furnace using a metal alloy. This too has recently been tested at large scale. And then this alloy is further processed in converters. And this is where a nickel, cobalt, copper matte is produced. Based on the technical reports or their PEA, these are the recoveries. So mid-90s nickel, somewhat suppressed for cobalt and copper. Listen to the video by the CEO of TMC, and he just made one comment that kind of got me interested again, and about he quote-unquote amazing recovery. Unsure if this is metallurgical recovery or something else, but I thought it was fascinating to hear this, and obviously keen to see the PFS results come out shortly, I think. Here's the flow sheet, and Ron, now that I know that you're online, you may recognize yourself here. That's you out there, and this is me a really very long time ago. But here's a flow sheet that's being used. So the nodules go through the biometallurgical steps. It leaches in an atmospheric and a pressure oxidative style leach. Copper is recovered here as cathode, and I threw this picture in here just to show that even though that right now I do a lot of talking, but there was a time where I still was doing actively test work, and this is myself and Ron both online here cleaning washing a copper cathode here. The atmospheric leach slicker is further processed, impurities are removed, solvent extraction is used to ultimately produce cobalt sulfate and nickel sulfate. Okay, and let's see if I can get to the next slide. So if I can summarize the smelting acid leaching flow sheet, there's a good outlet here for manganese. It doesn't contribute to the reagent consumption, but obviously it's been replaced with a highly energy intensive pyrometallurgical step. Although they'd probably say that the high energy intensity has been mitigated by the ability to select a site with low cost renewable energy. Slightly depressed metal recoveries, particularly for cobalt and copper, and the residues are recycled back to the smelter. So I'm going to switch topics here now and go to the next project. This is the reductive acid leaching route that's originally proposed by GSR. This is a subsidiary of the Belgian dredging company. Uses a patented process. It's a Umicore process, in fact. It's a single-step reductive acid leaching route using sulfuric acid and SO2 gas, and high recoveries. It's characterized by high recoveries of all four metals. We were contracted by them in 2021 to investigate this route, and so we've shown that we were able to get high recoveries, 99% nickel, cobalt, manganese, 98% for copper. We've done a bit of work on the back end of the flow sheet, the liquid treatment flow, part of the flow sheet, showing that we can get high recoveries of copper as a copper sulfide product. Nickel cobalt as an MSP, mixed sulfide precipitate, that's what that means. And there's a few novelties within the flow sheet, and the next slide has the actual flow sheet, but leached manganese is crystallized at elevated temperatures as a crude manganese iron sulfate product, which is then thermally decomposed to an iron manganese oxide, NSO2 for recycling. So here's this flow sheet. Here's the leaching step. Copper sulfide is produced with using H2S gas. A mixed sulfide precipitate, MSP as we call it, is produced using hydrogen sulfide gas. And here are the two kind of innovative steps here. So manganese sulfate is crystallized at temperature. This is not an evaporative crystallization step. This is heating it up. And these crystals are then pyrolyzed into SO2 gas for recycling and the production of a kind of a crude manganese iron oxide. A few summary notes on this. So high overall recoveries of copper, nickel, cobalt, and manganese, and the high reagent demand required because we're leaching all four metals is offset by the internal recycling of reagents. So the process includes a novel crystallization process, including a hot filtration effect step. It's important to note. And it includes this thermal decomposition step to recycle SO2 within the flow sheet. So the various products made out of the flow sheet that I showed here just now will require further refining. I'll talk a little bit about Kuprion here. This was considered by Seabed Resources, now Loki Minerals. And this is the process that was originally developed by Kennecott Copper Corporation, so hence also sometimes called the KCC Kuprion process. We piloted in the 70s, and believe me, this was the best picture I could find of that pilot plant. It's not a very clear picture. Various papers by alcohol describe the leach process chemistry very well. This avoids high temperature processing or any other kind of aggressive leach processes or conditions. The excipient is an ammonium carbonate liquor. And the cuprion name, by the way, is a wordplay of cuprous and iron. And the cuprous iron plays a really important role within this chemistry. We were contracted in 2020 to 2022 or so to pilot this particular flow sheet. It's worthwhile to kind of dig into the chemistry here a bit, and I'm going to try and simplify it a bit in the next few slides. To explain cuprion, I think it's good to kind of divide this into three main steps. And the first step is the reduction of the manganese dioxide, which is the bulk of the nodule, really, and really within this reduction, we kind of destroy the crystal lattice. And it's the cuprous iron that reduces the manganese from 4 to 2, and it produces a cupric iron. The actual reaction equation is shown here. And as the manganese structure is destroyed, this allows the leaching of copper, cobalt, and nickel in the lixiviant. So that's kind of the second step here. And the third step is the regeneration of cuprous using carbon monoxide gas. So cupric with carbon monoxide forms the cuprous iron that can be reused, and kind of the net overall reaction is shown here. Here's the flow sheet that is proposed. So the leaching step is shown here. Leach liquor is oxide, so cuprous goes back to cupric, and it goes through a solvent extraction step, electrowinning to make copper cathode, nickel cathode. And our work focused again on the leaching step, trying to understand this, and we've piloted this part of the process as well. And that's what the next 1 or 2 slides are about. But some of the key characteristics of the flow sheets is shown here. So the lixiviant is regenerated here. Manganese ends in the leach residue as a manganese carbonate that can be further processed into manganese metal or manganese sulfate. And copper and nickel are recovered as cathode. Here's a picture of this pilot plant. It was a small pilot plant, used one of our mini rigs here, and we did this in 2022. It's been well published and described by Professor David Dreisinger in 2022. We learned that we can get high recoveries of nickel, kind of mid-90s for copper. And cobalt had really interesting behavior. It started off quite high, but as we built up cobalt tenors in our leach liquor, the cobalt recovery decreased. And I think it got in our pilot plant as low as 60 or 70%. But some authors have reported cobalt as low as 30 to 50%. Okay, so trying to kind of summarize these 3 flow sheets here, they're all based on hydrometallurgy. The smelting hydromet refinery flow sheet by TMC uses pyrometallurgy to produce a manganese silicate. So it's got a good outlet for manganese and then produces the meth. Recovery is somewhat suppressed. The reductive acid leach uses sulfuric acid and SO2 gas and goes after or leaches all 4 metals, but uses the internal recycling via manganese sulfate crystallization and pyrolysis back into SO2 and MnO. And then I just spoke about the cuprion process using the ammonium carbonate lixiviant to go after copper, cobalt, nickel. And I guess with the new feed material, the energy intensity, suppressed recoveries, or perceived complexities related to new processes, I would consider that there comes a risk with this. And a little later in this presentation, I'll talk a bit more about the risks. Now, these 3 projects kind of went through our labs roughly at the same time, and we became interested here in doing and looking into some alternative processes. So we looked into high pressure acid leaching, HPALs we call it. This is a mature technology for nickel laterites, particularly the limonite fraction of the laterite. So this is low grade nickel, 0.1, 0.15% cobalt. There are various processing plants that use this technology in Cuba, Australia, Philippines, Madagascar, Turkey, Indonesia. Now I'll get back to the Indonesian one particularly. I think I've got a picture of one of the Philippines plants as well. Process conditions are listed here. There's a bit of old literature from the 70s and 80s on this, but it's a bit sparse, wasn't always very complete. Some have commented on selective extraction of nickel, cobalt, copper against manganese, and others have commented that there was significant manganese extraction. It wasn't quite clear. And because the literature was so sparse and showing this variable manganese behavior, we thought it would be useful to initiate a small internal R&D program using an available nodule sample. And our objective really was to provide proof of concept. Now, we're a service company, and we do work for our clients. So whenever we say, hey, we want to do some internal R&D, that may raise some eyebrows here and there, but we really thought we had a good case to be made. So our management were happy to let us go and try a few things here. So the next few slides are going to show a few test series that we've done. So you're going to see some of these graphs here where I'm plotting extraction versus the various metals, nickel, cobalt, copper, and then some of the impurities. And this slide here is our first test series that we ran, and it's trying to copy some conditions that were reported by this author here in 1988. There were different nodules. These were not CCZ nodules. These were, I think, Indian Ocean style nodules. Conditions are listed here. And although we got good rejection of iron and manganese, so low extractions, we liked that. We weren't quite happy with the extractions for nickel, right? We're in the kind of 60s and 70s, even at higher acid addition. So we weren't quite happy with these initial test results. And we quickly decided, okay, let's eliminate this oxygen overpressure. We were quite concerned that kind of contributed to the poor cobalt recoveries. We played around with pulp density, and that's really what this test series is about. And here we see, again, extraction versus metals here, that under certain conditions, we were able to get pretty high nickel extraction. We're close to 100%. Same for cobalt, same for copper. But we weren't quite happy yet with the rejection of these various impurities. But making good progress here. So ran another series of tests, reduced our acid addition further. We were operating at high pulp density, 30%. And this test we were quite pleased with. So we had high, almost quantitative extraction of nickel, 99%, kind of mid-low 90s for cobalt and copper. And we were able to show that we were able to reject the majority of our impurities. And those are the impurities that contribute to our reagent demand, manganese, iron, aluminum. We were able to reject those into the leach residue. Now, lots of room for optimization. It's not my role here to fully optimize these type of processes during an internal R&D program, but my role here was to show, hey, there is something out here that is worth considering. Leach slickers, hydrometallurgists on the call will say, oh, that's a nice liquor. That's grams per liter for nickel, cobalt, copper. We will know what to do with this. This is suitable for conventional processes. Now, the leach residue, it's of, I'd say, low-grade manganese ore, grade, so 31% manganese. And we did do some leach work on that residue. In a single test, we were able to show that we can recover 100% of the manganese using a mild reductive leach test. So some thoughts here on what this flow sheet might look like. High pressure acid leaching, so HPAL to go after nickel, cobalt, copper. We saw pretty good solid liquid separation, and particularly with the rejection of manganese and iron into the residue, that makes that residue heavier. It makes it easier to filter. Impurity control, such as iron and aluminum, can be done by a very conventional neutralization. Copper can go to copper cathode via SXEW. The little bit of manganese that is there, the 5 or 6% that's extracted, can be recovered. It could be processed into manganese sulfate. And it's actually of interest to note that if we go back to the 60,000 ton per year nickel style plant example, now this would produce, if all of the manganese that was leached goes to high purity manganese sulfate, now we're looking at around 225,000 tons per year of the manganese sulfate. Now, that is more in line with kind of current market examples of manganese sulfate producers. And I refer back to the E25 example that is making under 30,000 tons. With respect to the nickel cobalt, various options, MHP, that stands for mixed hydroxide precipitate, mixed sulfide precipitate, sulfur extraction, going into nickel cobalt cathode production. It's all possible. And I conclude again that HPAL, or I say again, HPAL is mature technology, maybe a lower risk. Picture here on the right shows the Coral Bay nickel laterite operation in the Philippines. In fact, piloted at SGS in Lakefield in the early 2000s. So my conclusion is, hey, HPAL is worth another look for this. There are some concerns, obviously. So what do we do with the leach residue? Where do we locate the plant? How would that be processed or stored? What do we do with the gypsum waste products? But worth another look. Okay, I'm going to switch topics here a little bit. I'm going to talk about de-risking, pilot plants. And I will, after a few slides, go back to deep sea mining and why this is all relevant. So just bear with me here a little bit. So why do we run pilot plants? It's to confirm the metallurgical performance. And metallurgical performance means that's recovering the grade of your product, reagent consumption under continuous operating conditions. Is there to observe the material handling, and I'll refer back to material handling in the next few slides. And I like talking about the operability of the flow sheet. So we want to see that the flow sheet that we've developed, is it robust? How does it respond to circuit offsets? How does it respond to different feed materials, so ore variability? So if we're able to operate a pilot plant successfully, this provides confidence that this can be repeated at commercial scale. We want to look at impurity buildups when process streams are recycled within the flow sheet. We want to produce samples for solid liquid separation testing, corrosion studies, potential other or potential offtake partners. And it's important to realize too that continuous testing is physically and chemically different from batch testing. That's the whole topic on its own, and happy to get into this maybe at the end or with offline. But I'll just roll out a few examples here. The morphology of precipitates made on the batch versus continuous are different. It impacts your solid liquid separation behavior. So it impacts the size of your thickener, filter, and hence your capex. It's really important. In solvent extraction, we see this in crowding effects. We need continuous testing to comment on organic stability. And ultimately, back to the main questions, why we run these pilot plants is to provide data into engineering studies, to de-risk your overall project and avoid prolonged ramp-up curves. And that's what the next few slides are about. So I'm going to some of you, and particularly all of the engineering firms online, will have seen these curves. Terry McNulty is an American engineer, former president, by the way, of Hazen Research, our competitor. And most of you would have seen his curves. Now, Terry analyzed various ramp-up performance of, I think it was around 80 plants or so. And he looked at smelters, concentrators, various hydrometallurgical flow sheets, and kind of characterized them in initially 4 categories. He's expanded this recently into 5 categories, kind of based on the maturity and complexity of the technology. So series 1, that's this particular line, kind of characterized by reaching nameplate capacity. So that's 100% of your design capacity. That's the 100% line right here. And this is years after commissioning. So a series 1 would kind of reach design capacity after 1 year. And what he concluded that these type of projects were characterized by mature technology, a really thorough understanding of the feed material, and extensive piloting. A test work was done as well. And there's quite a few other characteristics that doesn't really fit in the slide here, but I can only recommend to all of the kind of listeners here, read his papers. They're really good. On the flip side, Series 5, originally it was a Series 4, but called a Series 5 now. Complex, new metallurgy, a poor understanding of the feed, and very limited piloting test work done. And so what's the impact of this kind of extended ramp up? Well, additional capex required to fix all of the issues to kind of bring it up from here back up to there. Obviously, unanticipated operating expenses while you've got a fully staffed plant, delayed revenues, cash flow. But what I think is interesting to note is that his analysis is based on traditional commodities. And so how about this recent surge in critical materials, or sometimes called them non-traditional commodities, but also non-traditional feed materials? And with that, I really mean the black mass material from the battery recycling, but also the onshore processing of nodules, I think is really relevant in this conversation. So in the last few months, I took a look at some recent critical mineral projects. And I guess we can talk a little bit about what's a critical mineral. And well, it's a long list. The government of Canada has put half the periodic table on there, and they're shown here. I just want to highlight a few, and I'm going to show a few ramp-up curves of a nickel plant. I think it's got 2 rare earth plants. I think I've got a lithium plant and a vanadium plant. So in the last few months, I examined the performance of 13 plants that have ramped up in 2009 or later, though, kind of in the last 10 years. 12 of these are what we call critical mineral projects, and I put a gold project in there just for contrast. They're all based on hydrometallurgy. I'm not showing all 13 of these, but I'm going to show a few of them because I think it's worthwhile taking a look at the performance of these type of plants that are based on new flow sheets or new feed materials. Because sometimes not a pretty picture. Okay, the first one here is a lithium plant. This is a lithium refinery producing crystallized lithium hydroxide. It's the plant in just outside of Perth in Australia, ramped up in 2022. It's fed by spodumene concentrate. Flow sheet is kind of summarized here. First production 2022, and here's their ramp-up curve. It's a Series 5 McNulty. And then when I read through the various press releases that are out there and the operational updates, you kind of read in between the lines here. And their ramp-up is plagued by material handling issues, particularly around the acid roast feed system, filtration, and I understand there's quite some difficulties around the handling of the crystallized lithium hydroxide. Next one is a plant, and many of you will know that I'm a rare earth enthusiast, so this is a plant I've been tracking probably for close to 10 years. This is the Lynas rare earth plant in Malaysia, so this is the mine is in Australia, concentrator is there, but the concentrate is shipped to Malaysia and treated there through an acid bake impurity removal, solvent extraction circuit, and ultimately produces NdPr oxide. First production in 2013. It's a series 4, but has gradually increased to around 90% of design capacity. The reported issues, and they've put quite a few, how do you say, descriptions in various reports and press releases, but they could probably be summarized as material handling issues. There have been some issues around the acid feed mixing step, and I think I've got a picture on that on the next slide. I actually have data on how this plant goes further, but it's a bit trickier to kind of plot this in the graph, because at the moment this plant is receiving a mixed rare carbonate from the Kalgoorlie plant in Australia. Here's their acid feed mixing step, where they've clearly had an issue this particular day. The poor man has a jackhammer in his hand, and he's trying to, I guess, unplug one of these pumps or mixers that are shown here. So material handling, I guess, is the point that I'm trying to make here. Next one is another one of my favorites. This is the Mountain Pass operation in California, and there's a plant or a project where I've had some involvement as well, I guess I should say. And Mountain Pass deposits in California. They are processing a flotation concentrate. That's their stage 2 project. The flow sheet is summarized here, and that flow sheet or that plant was commissioned in 2023. This particular data point, it pains me to see it. I put it here last night. This was released 5 p.m. Eastern Time yesterday. It's the Q4 performance of last year, and I was really hoping that it was a little bit more here, but it isn't. Test work by SGS and others in kind of in the early 2020s, first production 2023. It's a series 4 or 5. Some of the issues, couldn't find that much data, public data on this, on some of the issues, but they pick up some damage to one of their thickeners. That's another one here, where this is vanadium. Now this is a Brazilian project, Americas deposits, Larco Resources still operates this project. It's a conventional vanadium flow sheet. Tested, by the way, also by SGS. In fact, I was the project manager for the Hydromet component of this work. So it's kind of neat when your own projects do get built and is operating successfully. Built in 2012, first production in 2014. SGS actually went back in 2016 and audited the plant. It's a series 2. It's currently at or well above 100% capacity. Wanted to throw in a nickel laterite one as well. I have 2. The other one will come a little later. This is the Gordes deposit in Turkey. Project developed by Metallurgical. It's a 3rd generation HPAL, but you could say this is kind of first in country in Turkey, and it's gradually ramping up. I guess at the moment still kind of a series 4 style plant. This was piloted at SGS in I forget the exact year. There are a few good papers on some of the issues that this plant experienced, and they have commented on the difficulties of the plant to respond to ore variability. Now, I said I looked at 13 plants. I didn't show all of the 13 plants, but I do summarize all 13 here, so some of these plants are not discussed here. But the kind of sobering conclusion here is that the majority of these are series 4 or 5. Now, there are other plants, obviously, and there's a few at the bottom that have done better, and I have a few comments on these. So of these 13 plants, 8 were kind of a series 4 or 5, 3 were a series 2 or 3. and only one was a Series 1. There was one that also had a slow ramp up, but it was really because of economic conditions. That's the Australian Kwinana nickel sulfate crystallizer. It had no technical issues. Those that were, and it's kind of interesting to dig a bit deeper here. I don't want to go too deep here. I do have other presentations on this where I go a bit more in depth. But those that were a Series 2 or faster, Largo, the Indonesian nickel laterite project, one of the Lithium Americas lithium carbonate projects, they were known technologies. In the case of nickel, Harita nickel, and I do show the curve a little later, it's a generation 4 H-spill project. They learned from Ramu and others. These were known technologies. Those that were the others, so Series 4 or slower, were new flow sheets, new process conditions, new in countries, such as the Gordes project in Turkey, or new flow sheet to the current team, because possibly some of the kind of institutional knowledge is just no longer there. And some of the common issues that I picked up, not with all of them, are material handling. Now, back to kind of the McNulty ramp-up curve. Terry says that very, and I quote unquote here, very carefully developed and executed project, they can ramp up quickly, and owners of new projects should avoid being too pessimistic in projecting early cash flows if they are certain that they've done their homework. So one example that I thought was worth pointing out, and this is the Harita nickel project. This is one of the recent Indonesian H-spill plant. This is I guess a 4th generation plant, and there's 3 of them, but I could only find the detailed ramp-up curve of one of them. I do know that the other 2, they ramped up similar speed, reaching nameplate capacity at or around a year. Big comments have been made that all 3 of these plants use the same engineering team, same vendors, and they learned from the Ramu plant, which is one of the other older Indonesian plants that did not ramp up all that fast. So again, I conclude there, hey, H-spill is robust, mature technology and should be considered for the treatment of nodules. So material handling is something that came up during a few of these slides. I want to go back to that and why this is so important. So I've got a few pictures here. This is in fact a picture of our rotary kiln here. This is a small kiln. It's a 6-inch diameter kiln, and no, this is not what we like to see. This one is clearly completely plugged, but instead we like to see something like this, where materials rolling nicely through the kiln, or like that, where it behaves like wet sand, or possibly like this when it's making more these large agglomerates. What I'm trying to make is that pay attention to the material handling. And we've seen in these ramp-up curves that that's often where it goes wrong. This is so important to examine when we're doing these test work programs for our clients. We like to operate mini pilot campaigns of select circuits in advance of larger integrated campaigns. We really feel that this is important. Okay, so I think I'm near the end here. So some final comments here that I'll read out. So I've spoken about several flow sheets that are under consideration for onshore processing of nodules, and I've spoken about what to do with the manganese. Where does it go? I think that high pressure acid leaching is worthy of a second or a new look. It provides high recoveries of nickel, cobalt, copper while rejecting many of the elements that contribute to reagent consumption. It uses mature technology. The ability to valorize some of the manganese as high purity manganese sulfate without flooding the market is of interest. Now, I spoke about de-risking projects and how critical this is to avoid potential plant failures. Seabed nodules are a new feed material and will require significant test work, bench, pilot, maybe demo plant to develop into successful projects. We like to say that value the project development phase like insurance. Invest to de-risk during the various stages of your test work program. Pay attention to material handling. It's an often neglected part of the test work, but it is so important. And as a more optimistic, on a more optimistic note, I should say, carefully developed, executed projects, they can ramp up quickly, provided you've done your homework, and we're here to help you all with that. Okay, I think that's it. Thank you very much for the attention. I'm happy to take questions.
Thank you. Thank you, Niels. So you can either raise your hand and I'll call on you, or you can type your question into the chat. So Jose, you want to go ahead and ask your question?
Yeah, thanks, Holly.
Mm-hmm.
Thanks, Niels. My name is Jose Benchetreat with Natural Resources Canada. Just thanks for the presentation. Super interesting. Not a technical expert at all in metallurgy, but I did have a quick question on it applies to the HPAL as well, but specifically on the 3 hydromet flow sheets for the manganese silicate residue, for the smelting and acid leaching one, for the manganese iron oxide for the reductive leaching, and then for the cuprion for the manganese carbonate. Do those residues, those manganese residues, are they the residues that still would contain all of the other impurities or metals in that structure? So I'm thinking particularly in the case of like rare earths that would exist in the nodules. Would those manganese residues be the ones that contain those rare earth elements? I hope my question was clear, because I'm not an expert in this.
Yeah, there are some low-level rare earths in the CZZ nodules. I'm not sure if they are of economic interest. Some of the other seabed minerals, such as the iron manganese crusts in the North Atlantic by Norway, they do contain higher levels of rare earths, where it might be of interest to go after them and extract and recover them economically. But to answer your question, don't think I actively tracked rare earths in this part of the work, but I do know generally how rare earths would respond under H-spill conditions. They would end up in the residue. Having run H-spill on other rare earth projects, I know typically it will not dissolve, or maybe if it does dissolve, it immediately reprecipitates. That's probably the more accurate way to describe it. So with H-spill, it would end up in the leach residue. The other 2 routes, I'm pretty sure it ends up with the manganese as well.
Thanks for that. Thanks.
Yeah, for example, within cuprion, rare earths are not expected to be soluble in an ammoniacal style liquor. If you smelt this, I'm pretty sure this end up in the kind of the manganese silicate stream. So that's where that would end up. But again, I don't think that would be of kind of economic value or interest. If you can dig this up in California, we're looking at 4 or 5% style concentration of rare earths in the ground. And here, these nodules, I think the CZZ, don't quote me on this, but I think we're less than 1,000 grams per ton. So it's not.
Okay, Niels, we have a question from Philip Mackey in the chat. He
Hi,
says,
Philip.
"Hi, Niels, all very interesting. Remountain Pass, is it still running, and does it produce a final pure product for the market?"
So I didn't get that question. What was the first part?
Oh, Read the Mountain Pass.
Yes.
Is it still running, and does it produce a final pure product for the market?
Yes. is the answer. The curve I showed for Mountain Pass was updated last night, taking the Q4 2024 data. This was data that was released at 5 p.m. sharp yesterday. The concentrator has been running for quite a few years already, Philip, and the bulk of the concentrate, as far as I know, is still shipped, sold into China, but a portion of that, and that's the stage 2 that MP Materials refers to, is treated on site, and that's the ramp-up curve that I showed. So this is a plant, stage 2 plant, that processes the flotation concentrate through a roaster, leach, various stages of purification, and ultimately makes an NdPr oxide stream. I added a line effect on that slide. I don't think I mentioned it when I was going through that particular slide deck that it is in fact producing NdPr metal right now, which is one of the steps required before you make a permanent magnet, right? So we make a mixed rare of oxide, and you separate these into the individual rares, NdPr oxides in this particular case. Then it goes through a metallization process to make metal. Then you have to make an alloy, and then ultimately you produce the permanent magnet. From what I can tell, based on their press releases, they are commissioning the production of NdPr metal at the moment. The curves that I put on the screen are related to the production of NdPr oxide. So that's the leaching, solvent extraction, separation, and finishing circuits. Hopefully that answers the question, Philip.
Unmute. Cool. All right, let's move to Kiran.
Hello, can you hear me?
I can.
Wonderful. Thank you, Niels. Wonderful presentation. In
Thank you.
particular, this McNulty plant ramp-up scale caught my eyes. And on slide number 38, there was a comparison of all different plants. And I was wondering what kind of energy level did they use? You know, was it a 1-2 megawatt class or a 10-20 megawatt class? And was it a natural gas, coal, or what kind of plant size they had for 100% capacity? Any idea?
Yeah, I'm not sure if I can answer that question. I'm just going to try and go back to that slide. I think this is the one you were referring to, right?
Right. And what kind of power level? You know, 10 megawatt class or 1 megawatt class? Or what?
I wouldn't have the foggiest idea, to be honest, with you. So I probably have I know I have the data on the size of the kind of production. I think Linus is, and I may be wrong. Someone please correct me if I'm misstating anything, but the Linus plant, I believe, is a 5,000 NdPr oxide, 5,000 ton per year NdPr oxide plant. MP Materials, I have the design capacity on this one as well. So I have all of that data, but what I don't have is the power consumption. I'm sure it's out there somewhere in literature, but I don't have this at the tip of my fingers.
No
Sorry.
problem. Thank you. Yeah, thank you.
Thanks, Kiran. Okay, we have a question from Claire, but I'm going to circle back real quick. Philip just said, Niels, just to check, some Mountain Pass product goes to China and some is processed at the site.
Yep.
Okay.
Correct.
Great. All right. So Claire's question, how does this, excuse me, let me start over. How does the sustainability of nodule processing compare with processing of other sources of nickel, copper, cobalt in a broad sense? Is there any reduction in energy needs in crushing / grinding steps?
Not sure if I can comment specifically on the grinding intensity. Studies have been done on that, possibly some by us. I just don't have the data right at my fingertips here. But there's lots of other things that go into kind of the sustainability aspects when you compare kind of land-based projects versus seabed-style projects. And this is a discussion that I've had with various people over the last few years. You know, if we're talking nickel, you know, we can talk about the harm done with limonite mining, particularly Indonesia. Cobalt, we could be thinking about the kind of human resource issues of human. I'm getting the right term, but the various issues in the Congo around child labor, etc., etc. But really specific to your question, I don't have this data right at my fingertips, but I know that exists. So, not really answering the question. Hopefully, it's good.
Yeah, I would like to just add one key point that at Impossible Metals, we've committed to be net zero for all of our commercial operations. That includes the actual mining, the operation of the robots, but also the mineral processing, which we will outsource. But we will either find something that is net zero, unlikely. More likely, we will pay to offset the carbon emissions from the refining process. But that's a commitment that we've made and have factored into our economic models.
Thanks, Oliver.
Great. Any more questions? All right.
Just ask a background question, and not necessarily to Niels. Who is Impossible Metals, and is this series only about Impossible Metals, or is it like you're saying that there's another thing, a seminar coming up about a webinar about BGR? Is that you, or is that somebody else?
Okay, let me answer this. So we host, Impossible Metals is a startup company that is building new robotic technology to access deep sea minerals in a very responsible way. We host these webinars, but they are not exclusively about our technology. They're about generally critical metals, and that's the broad topic, but with a little focus on deep sea minerals. And we will soon be creating a audio-only version of the same material in a podcast, so that if people are driving or working out, they can listen. And we do make all of this material freely available on our YouTube channel and soon to be on a podcast feed. But it's generally about critical metals, with obviously a slant on how deep sea minerals can be leveraged.
Thank you.
Great question, Ron. And I will, I'll send, once I post this, once I get the recording, I'll post it on YouTube, and I'll send the recording out to everybody who's registered for the webinar.
Oh, let me answer the question on the BGR. So BGR is a contractor. It's part of the German government. It's their marine research arm. They have held concessions in the Clarendon-Clipperton zone, and they've held them now for well over 15 years, I believe. And they are doing a test with us next year. So we have agreed to, they've agreed to allow us to test our next generation collector vehicle. We call it Eureka 3. And as part of that testing, because it's in international waters, you have to submit an environmental impact assessment a year before the test. We have submitted it, but we also have public consultation. So we present information in that very detailed document, and we invite feedback. And so the webinars on Tuesday, there are two, one in a European time zone, one in a North American time zone, are really focused on getting that stakeholder consultation and getting the feedback on the environmental impact statement. So the link is actually hosted on the ISA's website, and then it goes to an actual form where you can register. And we hope to also record and make them available as well.
Great. All right, we have a excuse me, a question in the chat from Deval Krishna. Is it economical to build a refinery in Pacific Island to save costs?
I don't think so. I would imagine that a processing plant would be built US, Canada, Mexico. There's other options, whether you ship directly east or southeast. There's a variety of options available. Reagents, human resources to operate the plant are present there, not necessarily on a small island.
All right.
Does that answer the question? Sure, whose it was?
Deval. Okay. I'm going to assume that's a yes then. Okay. Looks like our questions have slowed down. We're almost at 10 past. So I think we'll go ahead and close this webinar out. Niels, thank you so very much for presenting. And again, everybody, I will be sending the video, the link to the video on YouTube for the webinar either later today or Monday at the latest. So you'll be able to see it then. Great.
Thanks, Ollie. My pleasure doing this.
Yeah. Thank you so much, Niels, for doing this, and thanks everybody for joining.